This is a video on how to find the Riemann sum using right-hand endpoints on a function given an interval. So we'll start with a function, f of x equals x squared plus 2x. The interval being 0 to 3. And, one of the nice parts is when there's a 0 there, it makes it quite a bit easier. The algebra is easier. And obviously this function isn't too complicated, but the function really plays little role in it except for finding one piece. So first thing we need to do is find the delta x, which is the width of our rectangles. And we're going to take our b value, which is 3, subtract our a value, which is the 0, and divide by n, which is the number of rectangles. We get 3 over n. So that's the width of each rectangle. And then we're going to take that and we're going to find our endpoints. Now there's a couple of different ways we could do this. We're doing right-hand endpoints. So we're looking at the a value plus I times the delta x. I being the index, how many or which rectangle we're talking about. So we're looking for the first rectangle's endpoint. The I value would be 1. If we're looking for the 30th, it would be 30. If it would be the nth rectangle, the I value would be n. So we have a, which is 0. Again, this is really where it comes down to making it a lot nicer. We're adding nothing to I times our width. And that whole thing boils down to 3I over n. And that's the value then we would plug into f, 3i, or whatever our function is. So we're going to square that. And we're also going to multiply it by 2. We'll see what we get. And the result is 9i squared over n squared plus 6i over n. So that's the f of our endpoints, which is also the width of our rectangle. So we have, the height of our rectangle. So this is the height, that's the width, and if we multiply those, we would get the area of any of the rectangles. So let's do that. We have the width times the height and that's the area of any of the rectangles in my graph. Then I'm going to take them and I'm going to add up all of the rectangles. And I'm going to start with the first one and end with the last one, which is the nth rectangle. And we could use this formula to calculate any number of rectangles. So if we were looking at 10 rectangles, n would be 10, and we would calculate the area of each of those rectangles and add them together. That's what the sigma means, is add them together. But we don't want to do that. We want to do some calculus. Well, I want to do some calculus. So we're going to take the limit as n approaches infinity. It's going to take a little bit of work. So the first thing I'm going to do is break this apart. I want to get, I could distribute this, but I'm going to be factoring it out. So I'm going to just break these apart because of the addition. Okay, I know this is multiplying each of those, so I really could write it as sigma from 1 to n of 3n times 9i squared over n squared plus a sigma for the second piece, same values 1 to n, 3n times 6i over n. And we're still going to end up doing the limit of all that as n approaches infinity. Now, this is where we're going to kind of need some strategies because at this point, you may not even know what we're doing. So what we have to do is we need to take out of each of these expressions here, we've got to factor out all of the constant terms and all of the n's, because we're going to use some formulas, which I'm going to put on the thing here in just a second. So on the right, you can see those 3 new formulas. There's another one for, oops, messed up. That's supposed to be I squared. There's also one for I cubed. We don't need it for this example, so I'm not going to show it, but it basically takes all of the values in the highlighted formula. So n plus 1, and 2 squares each of those values, and that would be the formula for I cubed if you need it. We don't need it for this one, so here's what we'll do. Like I said before, we're going to factor out all of the n's and all of the constant terms, just leaving the I squared. So this is going to be 3 times 9 is 27, take that out, and n cubed, take that out. And what's left is the sigma from 1 to n. I'm kind of running out of room, so I'm kind of tightening it up a little bit here, of I squared. And the next piece, the constant terms would be 3 and the 6, which would give me 18, and there's an n and an n, so that's n squared, and the sigma would be from 1 to n, and all that would be left inside is the I. And the reason we do that is because we have these formulas on the right, which we can then substitute for the sigma pieces. So this piece right here is going to go away, and that piece is going to go away. We're going to replace them with, we're going to substitute the values that are on the right. So if it's I squared, this whole piece is going to become n times n plus 1 times 2n plus 1 all over 6. Now I'm going to keep that, I'm going to keep the 27n cubed in front of it. And the other piece, I, the formula for the sigma of I from 1 to n, looks like that. And I'm still going to do the limit of all of that stuff as n approaches infinity. So what we have done is we've taken this sigma problem, got rid of the sigmas, and now we have a limit problem where we have only n's and only constants. So this is now an n behavior situation. So what I tend to do is I kind of hope that people have learned about n behavior, because if you take a look at that first chunk, it is a lot like, I don't really need all of the pieces, but it would be 27n to the third over, I'm sorry, not 27, but 54 n to the third over 6n to the third. And then the second piece is going to be 18n squared over 2n squared. And if we make those n values extremely large, all of the extra stuff that would happen if I had expanded my numerators in each case, I'll just kind of focus on this one really quick because it's an easier one to expand. That would be n squared plus 1. And if I distributed the 18, I'd have an 18n added to this piece. Now, when I plug in infinitely large numbers, that 18n is insignificant. So I don't even think about it. I don't even worry about it. All I do is think about these situations. And if you understand n behavior, if you have an n to the third up top and an n to the third on the bottom, they essentially cancel each other out when you're talking about n behavior, or the limit as n approaches infinity. So it's going to reduce to just the coefficients in this case. So 54 over 6, which is 9. And the same thing is going to happen on the other one, n squared over n squared. If I plugged in infinitely large numbers, those are going to cancel. And I'm also going to get 18 over 2, which, I'm sorry, is also 9. And if you just add those together, you get your area. And it's an exact value. And that's the Riemann sum for that specific situation.